recently we were looking at limit cycles, which means isolated periodic orbits. One of the few and well-known results for 2D vector fields is this thing called the Poincaré-Bendixson Theorem. So I'm just showing what I wrote last time. It establishes that a closed orbit exists. You basically establish a region, R, called the trapping region. We assume that the vector field is continuously differentiable on the trapping region. The trapping region does not contain any fixed points. You also need to establish that there exists a trajectory that's confined to the trapping region. The main way that we do that is we find boundaries for this region, so like an outer and an inner boundary, where the vector field is pointing inward. And if you can establish that, then you know that there must be this trajectory C that's confined to the region. Because if something falls through the boundary, there's no going out, so it stays inside. This establishes that there's a closed orbit in the region. So the typical approach, like I said, is you call R a trapping region and you construct boundaries for it. So it looks like a deformed annulus. On the outer boundary, things are going in. On the inner boundary, things are also going in. You first set up a trapping region, but you also have to establish that there's no fixed points in R as well. So we're going to try this on some examples. If you remember from last time, we looked at a system in polar coordinates. It looked like that. In this case, because there's no coupling between the R and the theta directions, you could look at just the vector field in R, and this would look something like that. So there is a stable point at R equals 1. And so there's a limit cycle at R equals 1. We didn't have to use any fancy Poincaré-Bendixson or anything. We could modify this a little bit so that this part's the same, but then we'll add on plus mu R cosine theta for mu greater than or equal to 0. And then theta dot is the same. So then this would be the case up here for mu equals 0. So for mu equals 0, we already know that there's a limit cycle by some other argument. But now we've got this term, and it couples R and theta because of that cosine theta. So can we establish that there is a limit cycle? We could use the approach of the Poincaré-Bendixson theorem. And in this case, if theta dot is a constant, it's 1. And if we could find two radii, let's say this one is R max, and if the vector field is pointing inward on R max, and then there's an R min, a minimum radius, and if the vector field is pointing outward, then we've established a trapping region. So we could seek a radius R max where for things to be pointing inward, we need that R dot is less than 0, and an R min where R dot is greater than 0. That'll give us what we're seeking. And there's no fixed points because theta dot equals 1. So everything is moving in a counterclockwise direction overall. So there's already no fixed points. So as long as we can find this R max and R min, then we're good to go. So let's look at that and see if we can set that up. Well, cosine theta, we know, goes between -1 and 1. So it's less than 1, greater than -1. So if we write R dot, let's rewrite this. Notice we could pull out an overall R. R is greater than or equal to 0. We get 1 minus R squared plus mu cosine theta. Let's start with R max. For R max, we want the thing in the parentheses to be negative, even when cosine theta is as large as it can be. If cosine theta is as large as it could be, that means we've got 1 minus R squared plus mu. We want that to be negative. So for this to be negative, we need R max is equal to square root 1 plus mu. I should be more careful with the signs here. We want R max something greater than square root 1 plus mu. Say 1.001 square root 1 plus mu. Everywhere along the contour of R max, we'll have R dot being negative because the thing in the parentheses in here will be less than 0. Of course, R is positive, but that'll give us negative r dot. So by a similar argument, we can choose r min. Again, being careful about these equalities. We want r min to be less than square root 1 minus mu. So it looks like we should probably restrict ourselves to look only at mu less than 1. But if we have r min less than that, that means the thing in the parentheses, you put in cosine theta equals negative 1, and you'll get that r dot is positive. Use r min 0.999 square root 1 minus mu. For the Poincaré-Bendixson to be the most helpful, we want the size of this annulus to be as small as possible, because that tells us, all right, definitely inside here, there's going to be some closed orbit. So that's sort of what I'm going for here. That's it. So by the Poincaré-Bendixson theorem, we've got a closed orbit. There's a closed orbit somewhere in the annulus given by r less than r max greater than r min. And we could even numerically verify this. I'll do a numerical example with a phase plane plotter, something pretty big, just to show the power, because you can't even actually see how it's different than the mu equals 0 case unless mu is pretty big. So let's do mu 0.9. When I transform this system into Cartesian, so I could use it in a standard phase plane plotter, I pick up some additional terms than what I had last time. So this is in Cartesian. And you can see there's that 0.9 times some things. Those are what show up when you transform into x and y. I graph the phase plane, and I get this. This won't let me just draw circles of r min and r max, but we could try initial conditions and see where they go. So here's an initial condition starting outside. You see we've got some kind of deformed circle. It's a limit cycle. So it looks like there is a limit cycle. Here, the annulus would be pretty big because I used mu of 0.9. So 1 minus 0.9, square root of that, and 1 plus 0.9. So we've got a pretty big, but there it is. It's convenient to use Poincaré-Bendixson, especially when you've got things written in polar coordinates. But often systems are not going to be written in polar coordinates. So what do you do then? And you've got to use some other set of arguments. So that's one example. We could look at another. This is a biological example. It's more of a biochemical example. It's a biochemical oscillator. Well, that's what has yet to be proven. So this is a biochemical process called glycolysis. And this is how living cells obtain energy by breaking down sugar. There was excitement about biological oscillators because it was thought, okay, if there's these chemical reactions that can form oscillations, maybe that's a fundamental chemical basis for oscillations seen in different types of behavior in biological systems, like day-night cycles, heartbeat. Glycolysis, there have been some simplistic models proposed about how it works. So don't worry about the details of the model I'm going to put here. It's more just the idea. When you put the equations of motion in dimensionless form, you get something that looks like this. So this is x dot, is negative x plus a y plus x squared y. Y dot is parameter b minus ay minus x squared y. And here a and b are both parameters. They're kinetic parameters that are greater than 0. This is a chemical reaction rate equation. Here x, it's a non-dimensionalized version of the concentration of ADP, not the more famous ATP. This is adenosine diphosphate. And then y is the concentration of F6P, fructose 6-phosphate. So here's the system, and we want to know, are there oscillations? Is there a limit cycle? Is there a limit cycle for all sets of parameters, right? We got a 2-parameter system here. So let's see if we can construct a trapping region. You could look at this and say, oh, okay, maybe there's a way to write this in terms of polar coordinates, but there's not. Don't even try. We could use the process of finding Nullclines. So I haven't mentioned Nullclines yet. We're going to use Nullclines. These are curves along which one of the velocities is equal to 0. And these can be helpful. So there'll be the x dot equals 0 nullcline and the y dot equals 0 nullcline. We can plot those. So when you know that, let's say, x dot equals 0, that means the vector, here's a vector, the vector is only in the y direction. So it's either pointing up or pointing down. And same for the y dot equals 0. Y dot equals 0 means that there's no y component to the vector. So along those curves, things are either moving one way or the other way in the x direction. So we could do that here. If we write the nullclines, right, what do we get? The x dot equals 0 nullcline. We just set the x dot equation equal to 0, and then we could rewrite it. It's probably easiest to write this as y equals some function of x. Y equals x over a plus x squared. The y dot equals 0 nullcline is another curve. Y equals b a plus x squared. So let me plot the phase portrait. Concentrations are greater than or equal to 0. So we only have to worry about the x and y first quadrant. And we can sketch these curves, hopefully. The x dot equals 0 curve would be, we have some experience plotting this before. We had something where it was x over 1 plus x squared. So that thing starts out growing and then it shrinks. So we get something that looks a bit like this. It reaches some peak and then it starts to go down. And everywhere along there, this is the x dot equals 0. So there's no x component to the vectors. I will put in some lines, but I won't specify yet which direction the arrows are going. Okay, so this is the x dot equals 0 nullcline. Y dot equals 0. Instead of x on top, it's got b. So at x equals 0, this starts out at b over a. And it just goes down. It goes down differently. The details of how it goes down are depend on a and b. But for large x, it's actually going to be lower than the x dot equals 0 nullcline. And along there, the vector field is just pointing horizontally. Again, we don't know what direction to put the arrows yet. We can maybe figure that out at some point. So what do we do? In fact, all we need to know is the arrows at just some point, and we could probably figure out all the rest. I don't want to hide that equation up there. Think of x and y both being large. If they're both large, then x dot is going to be approximately x squared y, and y dot is going to be approximately negative x squared y, negative of the same thing, which means far away up here at very large x and very large y, this is pointing down, the vector's pointing down at a 45-degree angle. And just by knowing that arrow by continuity, we can find out the way the other arrows are going, right? So this curve here, the arrow needs to be pointing that way by continuity. If that was the y dot equals 0, that means that over here, y dot is less than 0. And to the left of that curve, y dot is greater than 0. And what else do we know? We know x dot. X dot in this region is greater than 0, which means below that x dot equals 0 nullcline, it's less than 0. It's sort of like a dividing line. So, right, so down here, x dot is less than 0. And we've got these 4 different regions which give different signs of what x dot and y dot are. And we can even put all the rest of the arrows here. That's going that way. Here, x dot's less than 0, x dot less than 0. This is y dot less than 0, y dot less than 0. We can get an idea of what the vector field is doing. We still don't yet know how to turn this into a trapping region. Maybe we have some idea. What we want to do is basically, in sort of a small form, we're going to do some weird shape. And say that this is the outer boundary. The x and y axes will form the bottom part, and then we'll have something of slope 1, -1, I mean. To make this an actual trapping region, it's got to be topologically look like an annulus, which means we'll have a little hole. Where will that hole be? The hole will be centered on this fixed point, right? Where the x dot equals 0 and y dot equals 0 nullclines meet. That means x dot and y dot are both equal to 0. So that's a fixed point. So we need to exclude that from our region, definitely. But then to get how the arrows are moving along that curve, that's just related to the stability type of that point. So think of an infinitesimally small circle surrounding that fixed point. If that fixed point is an unstable fixed point, then the arrows will be pointing into our yellow trapping region. If it's a stable fixed point, things are pointing in, and we don't have a trapping region. So it looks like there's going to be some dependence on what the stability type of that fixed point is. First, let's set up the outer contour. We've already established that far away for positive x and positive y, we've got vectors that are moving on a slope of -1. Now we kind of want to know, as we get closer to the action, I guess closer to the fixed point, does this slope get steeper than -1? And we can actually figure that out. So let me redraw this. Here's a trapping region that we could use. Let's start with this point up here on the y-axis. We'll move out a little bit until we are just above where the fixed point is. And you could figure out where the fixed point is. The fixed point is where this curve and this curve meet. And if you notice, they have the same denominator, so they meet at x equals b. So this is I'll call it x star. That's the coordinate of the x coordinate of the fixed point. So that's equal to b. So we'll stop here at b over a. So we're just making a horizontal line, and then we'll go down with the slope -1 until we hit the y dot equals 0 nullcline. So let me plot that nullcline again. This is hard to do. Okay, how about that? And then it steeply goes that way. All right, and then the x dot equals 0 nullcline. I need to make it intersect there. And then we kind of go that way. All right. So until we hit that x dot equals 0 nullcline, and then we'll draw something going down. So as an outer contour, does this work? Well, just look over here from the nullclines. This is pointing this way, so we've got a vector field that's pointing inside, at least on that bottom part. It's not exactly clear what's happening up here, but we could verify that in this region where we've got the top part of the trapping region, x dot is greater than 0 and y dot is negative. So that's also pointing inside. Maybe it's not as steep as I've shown it here, because we're really close to this nullcline where things are going that way. So maybe this is just kind of shallowly going in that way. So that works. But what about this 45-degree line? Like we showed for large x dot and y dot, we get that dy over dx, that's y dot over x dot, is -1. What about for smaller values? In fact, in particular, we want to know, are things pointing inward along that diagonal line that I've drawn? So we can compare the magnitude of x dot and y dot. In fact, let's compare the sizes of x dot and -y dot. So we could do that by writing x dot minus y dot. And then from the formulas up above, you'll notice there's things that cancel. Like the most annoying term that's cubic is going to cancel. I mean, it's order 3, x squared y. right? Because x minus y is just x dot plus y dot. So what do we get from that? We'll actually get b minus x. And from this, we get that negative y dot is greater in magnitude than x dot if x is greater than b. So that's why that point was chosen. So that means slope of vector steeper than -1. So that means along this curve, this is steeper than -1 along the whole curve. What about the other axes? Well, we could look at what's x dot and y dot when we're along the x and y axes. So if we were to draw, say we're choosing these x and y axes, it's the other part of this. The arrows are pointing, as we could figure out even from the Nullclines and things, the vectors pointing inward. So we've established the outer part of our trapping region. I don't know what this shape is. It's 5-sided. So this 5-sided outer contour is trapping. Got the vectors pointing inward. And then, like I said, we need to puncture that right where the fixed point is and find out what's the stability of that fixed point. If it's unstable, then we've got a trapping region. So that fixed point, if you solve for what the fixed point is, fixed point at intersection of the Nullclines, we call this x star, and then the y component, y star. We have x star equals b, y star equals b over a plus b squared. Now what do we need to do? If we were to get the Jacobian, so the Jacobian matrix for our nonlinear system, so the Jacobian at any point is -1 plus 2xy a plus x squared, -2xy, -a plus x squared. If you evaluate that at the fixed point, right, what we want to know is the determinant and the trace. So at the fixed point, the determinant is going to be a plus b squared. And because both a and b are positive, this is positive. The trace is a bit more complicated. It's -b to the 4th. This is all over a plus b squared. -b to the 4th plus 2, parentheses, 2a minus 1 b squared plus a squared. So if you think of our drawing from before where we classified fixed points, we have there's the delta axis and the tau axis. So we know we're somewhere in the positive delta. So it's not a saddle point. But if we have negative tau, that was stable fixed point, which means the arrows are pointing inward, and positive tau was an unstable fixed point. We could set this equal to 0 and find out what's the dividing line. Tau equals 0. Tau equals 0 occurs when that numerator equals 0, and you could write that b squared equals 1/2 1 minus 2a plus or minus square root 1 minus 8a. This defines a curve in the parameter space of a and b that I'll sketch. Remember, they're both positive. We've got a and b. This is 1. There's some curve that has a shape kind of like this. It's kind of like a sideways parabola. And tau is greater than 0 here. Tau is less than 0 here, right? And along this curve, tau equals 0. This goes out to about 0.12 in A. So in this region where tau is greater than 0, we've got an unstable fixed point, which means we would have a limit cycle by the Poincaré-Bendixson theorem. Yeah, since the arrows are pointing inward, it's a stable limit cycle. So we have a stable limit cycle. And then outside of that, we have a stable fixed point. Does that make sense? Right? Because when tau is greater than 0, then for the kind of inside puncture, arrows are pointing outward. I should draw arrows. We don't really care exactly how they're pointing outward. They're pointing outward. I don't care if they're spiraling or what. As long as they're pointing outward in an infinitesimally small puncture to this disk, that's around the fixed point. Then we've got this weird 5-sided thing where things are pointing inward. So that's how you would do it for this system. Let me, like before, do a numerical example that's in the range that we want. Let me pick something here. Let's do a numerical example. A is 0.08 and B is 0.6. So based on this analysis, we should have a limit cycle for this system. There it is. I'm only plotting the first quadrant. If I graph the phase plane, here's some arrows. And you can even see here, looks like the arrows are pretty uniformly going in a slope of -1 far away from the origin. And let's just take some initial conditions and see what's going on. Looks like everything is going to some stable limit cycle. So it's good to verify with some computer-generated phase portrait. These are 2D autonomous systems. The Poincaré-Bendixson theorem, it's basically saying there's nothing more complicated is possible than a closed orbit. Like that's, in some sense, the most interesting type of thing that you could get in a 2D system. You can't get other types of behavior. There's no chaos in the phase plane. An n equals 2-dimensional system. There's no Poincaré-Bendixson theorem in 3D. It crucially depends on being 2D. So in higher dimensional systems like n greater than equal to 3, Poincaré-Bendixson theorem no longer applies, and you can have something radically new happen, which is that trajectories can wander around forever in bounded regions of phase space without actually settling down to a fixed point or a closed orbit. In some cases, the dynamics settle down to something that has a fractal dimension called a strange attractor. Let me just say that Poincaré-Bendixson doesn't apply in n greater than equal to 3, and new phenomena like chaos can occur. Also, endless wandering of trajectories in bounded regions without settling down to a fixed point or closed orbit. That's phenomena that's possible. You can, of course, still have things settling down to fixed points or closed orbits, but you also get new things. Good to know.